Scientists superheat gold to 14 times its melting point. Imagine heating gold to a temperature 14 times higher than its melting point, and yet the metal stubbornly remains solid instead of melting into a liquid. This astonishing phenomenon was recently achieved by scientists using ultrafast, high-intensity lasers, opening new frontiers in the study of extreme states of matter. In a groundbreaking experiment detailed in a study published on July 23 in the journal Nature, researchers successfully superheated a thin film of gold without it transitioning into a liquid. This breakthrough defies a decades-old theory about how solids behave when heated beyond their melting points, while also providing the first precise method to accurately measure temperatures in incredibly hot systems. Extreme states of matter, like the plasma enveloping the sun, or the crushing high-pressure cores deep inside planets, can reach mind-boggling temperatures measured in millions of degrees Fahrenheit. Yet, one of the biggest challenges for scientists has been how to reliably measure the temperature of such warm, dense matter, which exists for only fleeting moments and resists easy quantification. While we have effective ways to measure density and pressure in these hot materials, temperature has always been an elusive quantity, explained Bob Nagler, a co-lead author from the Department of Energy's SLAC National Accelerator Laboratory. He pointed out that previous temperature estimates carried enormous uncertainties, hampering progress on theoretical models for decades. The key to overcoming this challenge was speed. The team employed incredibly brief X-ray laser pulses lasting just 45 femtoseconds, that's 45 quadrillionths of a second, shining them on the gold film to rapidly heat it. As the X-rays pass through the crystalline gold, they cause the atoms to vibrate at frequencies tied directly to their temperature. The researchers then fired a second laser pulse that scattered off these vibrating atoms. By analyzing the change in frequency of the scattered light, they accurately calculated the atom's speed, and consequently, the material's temperature. But here's where things get truly surprising. The experiment revealed that gold can remain crystalline at a searing temperature of 19,000 kelvins, about 33,700 degrees Fahrenheit, or 18,700 degrees Celsius, astonishingly 14 times its standard melting point of 1,337 kelvins, 1,947 Fahrenheit, or 1,064 Celsius. According to Thomas White, Associate Professor of Physics at the University's Nevada, Reno, and study co-lead, I expected the gold to heat significantly before melting, but not an increase of 14-fold in temperature. This might be the hottest crystalline material ever recorded. Under normal circumstances, solids melt into liquids at a defined temperature. Sometimes, however, materials can enter a state called superheating, where they surpass the melting point without changing phase. Most people encounter this when heating water in a microwave. The water doesn't immediately boil even after exceeding 212 degrees Fahrenheit, 100 Celsius if the container is smooth and free of imperfections that serve as bubble formation sites. But a small disturbance can cause the superheated water to suddenly and violently boil. An explosive end to this delicate, metastable state. Back in the 1980s, physicists posited a theoretical boundary for superheating solids, only about 3 times their melting point, termed the entropy catastrophe. At higher temperatures, according to this theory, a solid's entropy, a measure of disorder, would outstrip that of its liquid form, violating the second law of thermodynamics, which insists that disorder must increase. In other words, a neatly ordered solid couldn't be more disordered than a liquid. Such a scenario was considered impossible. So how did the gold defy this entropy catastrophe and stay solid at 14 times its melting point? The researchers believe the answer lies in the exceptional speed of heating. The gold's crystal lattice didn't have time to expand or rearrange during the unimaginably brief period of heating, within trillionths of a second, which prevented the usual transition to a liquid. White was quick to emphasize, we didn't break the second law of thermodynamics. Instead, we demonstrated that these theoretical catastrophes can be avoided if the heating happens extremely fast, as in our experiment. This insight pushes our understanding of matter under extreme conditions and highlights the importance of timescale in phase transitions. But here's the thought-provoking part. Could this discovery lead to rethinking other phase change models that assume equilibrium conditions? And what implications might this have for materials science, astrophysics, or even industrial applications that involve rapid heating processes? What do you think? Does this shatter old physics dogmas, or does it simply highlight the complexity of nature's behaviors under extremes? Share your views and join the conversation. About the author, Victoria Atkinson is a freelance science journalist with a passion for chemistry and its intersection with both natural phenomena and human technology. Based in York, UK, she brings her expertise from previous roles at the University of Oxford and Chemistry World to uncover and explain the fascinating tales behind scientific discoveries. Holding a D.Phil in organic chemistry, Victoria's work spans diverse scientific fields, making complex ideas accessible and engaging for all readers. Gold survives 19,000 K. Entropy Catastrophe debunked by Ultrafast laser shock. Breaking the rules of physics, Gold's incredible heat-defying experiment. In a groundbreaking scientific revelation that sounds lore like science fiction, researchers have pushed the boundaries of material science by heating gold to temperatures that defy every known thermodynamic prediction. Imagine a substance remaining solid at temperatures 14 times hotter than its typical melting point. Sounds impossible, right? Yet, that's exactly what just happened. The shocking discovery that's rewriting textbooks. Scientists have achieved something extraordinary. They've superheated gold to a mind-boggling 19,000 Kelvin without causing it to liquefy. To put this into perspective, that's like taking a metal that normally melts at around 1,300 Kelvin and subjecting it to temperatures comparable to the surface of the sun, while keeping it in a solid state. But here's where it gets controversial. This experiment completely challenges our understanding of material stability and entropy. The cutting-edge technique, ultrafast laser heating. Traditional scientific wisdom suggested that when a solid is heated beyond 3 times its melting point, it should become thermal. Gold superheated 14 times melting point, defying entropy catastrophe theory. In a groundbreaking experiment, a team of physicists heated a thin gold sample to an astonishing 33,740 degrees Fahrenheit, higher than the sun's surface, and it didn't melt. This feat, known as superheating, not only shattered records, but also disproved a 40-year-old theory about the limits of superheating in solids. The international team of scientists, led by Thomas White from the University of Nevada, Reno, used a laser to superheat a 50-nanometer thick gold sample. They then measured the temperature by firing a pulse of X-rays at the sample and analyzing the change in frequency of the reflected X-rays. This method allowed them to directly measure the gold atom's velocity and temperature for the first time. The gold reached a temperature of 19,000 Kelvin, which is more than 14 times its melting point of about 1,300 Kelvin. This achievement was unexpected, as a long-standing theory from the 1980s suggested that superheating of solids could not exceed 3 times their melting temperature, a limit known as the entropy catastrophe. However, the gold sample surpassed this limit, and the team believes that the speed of heating, which occurred in just 45 femtoseconds, prevented the gold from expanding and melting. This finding challenges the conventional understanding of thermodynamics and opens up new possibilities for studying warm, dense matter, such as the cores of planets and human-made fusion reactors. The study's lead author, Thomas White, expressed his surprise at the results, saying, "We were totally shocked when we saw how hot it actually got." The team's work did not disprove the second law of thermodynamics, which states that disorder increases with time, as the gold atoms reach their extreme temperature before they had time to become disordered. This discovery has sparked renewed interest in a question that researchers had considered solved nearly 4 decades ago. How hot can something really get before it melts? If materials can be heated quickly enough, there might be no limit. The team's new approach provides a method to accurately measure these temperatures, paving the way for further research into the properties of warm, dense matter. The implications of this research are far-reaching, as it could lead to a better understanding of the conditions inside planets and fusion reactors. The team's work has also sparked controversy and debate in the scientific community, with some experts questioning the implications for thermodynamics and the limits of superheating. What do you think about this discovery? Do you agree with the team's interpretation, or do you have a different perspective? Share your thoughts in the comments below.